Hello. Today I'm going to upsolve problem D from ICPC World Finals 2011 in Orlando. Chips challenge. First of all, let's get acquainted with the statement. We have some microprocessor company and it makes chips. Each chips is like an n times n square of slots, and each slot might be either empty or disabled if it's filled with a slash, or finally it's already filled with a chip. In this case, where it's C there. There are several conditions. First of all, in the first row, the number of chips should be the same as in the first column in the end. Yeah, for example, here we have the solution to this test. W indicates the added chips. So we see that we added one chip in the first row and two chips in the first column. So in the end we have both in the first row in the first column 3 chips. In the second column and in the second row there are 2 chips. Then we have 3 chips in the third column and in the third row, 2 chips in the fourth, 3 chips in the fourth, and finally 2 chips in the fifth. And also, there should be no more than A over B of the chips in any row and in any column. So this is the problem. If this is possible to do, we should output the arrangement. Otherwise, we should print that this is impossible. So this problem is definitely looks like a flow problem. This is not a coincidence. This is really a flow problem. At first, I even thought that it is sort of linear programming, but the most famous linear programming problem is a flow maximal flow problem. Okay, so let's imagine that we have several vertices for rows and several vertices for columns. Actually, this is what I thought of during the contest, but we didn't have time to write it and check it. So we already have several chips which are activated, and it is a common idea in both mathematics, Olympiad mathematics, competitive programming, that actually if you have some grid, this is actually a graph between rows and columns, and you have each edge in this graph corresponds to some cell in the grid. So this is very important idea which comes very often, which you see and you solve problems with it. So here we have a graph. So first of all, if we have a slash, it's easy, just no edge between R and C, Ri and Cj. If the cell ij is filled with a slash. After that, let's consider ij where there is an edge between I and j. So there is a chip. In this case, we draw an edge. And if we already think in terms of flows, this is kinda... If we start, okay, with the dot, This is like an edge going from Ri to Cj. This means, and its capacity is 1. It means you can bring 1 unit of flow through this edge, but you can direct no flow at all if you want. And C means that you have to, there is an edge of capacity 1, and you have to direct 1 unit of fluid during this, not during, but through this edge. So slash means that there is no edge at all. Dot means that we can direct 1 unit of flow or 0 units of flow. This means just an edge. And there is also some sort of mandatory edge, which is out there and which forces you to direct 1 unit through it. So there is also some sort of condition that the flow through Ri should be equal to the flow through Ci. What this means is actually we can connect C first with R first, C second with R second, etc. What will it mean? So some sort of flow comes into this vertex, all this flow goes here, all this flow goes here, and after that it dissipates from this vertex. And kind of circulations motifs are here. So circulation is a, how is it called? It's a system where for each vertex the sum of flow which comes into it equals to the sum of flow which comes out. So if we calculate like divergence in terms of mathematical physics, it is always 0. So in this case, we just have it. We need to, like, outcoming from Ri should be equal to the flow going through this edge, and the flow through this edge should be equal to the flow coming into the vertex Ci. So we have Ci equals Ri because of that. Okay, this is still a circulation. There are no, like, there are no conditions of maximizing something, okay? Let's start with circulation. We need to check whether in this graph there is a circulation. Okay? If there is a circulation, then it is just actually possible to put some chips somewhere. And if there is no circulation, then the answer is impossible. Also, what about these two conditions? Yeah, first of all, this condition is already okay. We have also this condition which we didn't work out what to do with it. So it says that there can't be any row or any column through which the flow is greater than AB of total flow of total number of chips. Okay. So if we knew the total number of chips, we could just put them as capacities of these edges. So it would be AB times total. AB times total. But it is impossible. We cannot do it. So instead, we can just fix, we choose the capacities of all these edges. Let's call them, I don't know, D. D is the capacities of all green edges. And after that, we find the maximum flow So the maximum sum of flows through the green edges. And what we want is the total to be at least A over B times, no, B over A times D. So now we have a circulation, but in which we need to maximize something. This is hard because usually you just check whether a circulation is possible or not in some transport system. And here we need not only to check the ability to make a circulation, but also to maximize the flow through green edges. And if it's maximized, we now check that total is at least B over A times D. And after that, the answer, the total number of chips, is just total, maximum total among all possible tries. But then we need to subtract Z, where Z is the number of already put chips. Because in the problem you are asked to find the maximum possible number of chips which you can add into the graph, into the system, into the chip. Maximum number of widgets which you can add into the chip. Okay, that's gonna be added. So we need to subtract the widgets which are already there. This is called Z. Okay. The problem is how to find the maximum circulation with maximum sum of green edges. Actually, I don't know if I can do it in general case, but in this case I can just reduce it to some flow problem. So let's again work this out. We have R from R1 to Rn. We have also C's from C1 to Cn. Let's do something. So again, first of all, so we are checking whether it's just possible. So first of all, we just need to check that with bandwidth D, this is possible. So how do we do it? So we take D. So first of all, we connect all these pairs with bandwidth D, etc. Okay, this means that we cannot have any row or any column greater than D. And also this says that Ci equals to Ri, where Ci and Ci are the flows from Ri and to Ci inside this chip. What next? If we have a slash somewhere, then the corresponding vertices are just not connected in any way. Also, if we have some sort of vertices which are connected with a dot, in this case we connect them with an edge of capacity 1. This means that we can direct one unit of flow from Ri to Cj, or we can not send this unit. And in either case, this would be fine. So we are allowed both to put the chip there or not to put. So how do we deal with C's? Okay, in this case, instead of making an edge, we do the following. We create a special vertex S, which is called source. And we also create a special vertex T, which is called sink. So we say you have to direct one unit of fluid into this vertex. Okay, so if these are two vertices which correspond to some chip no, to some widget Cij, which is already put here. We say that we need 1 unit from S to this vertex. Okay. And 1 unit from this vertex to T. Okay. After that, we just check whether there is. We just try to find the maximum flow. Okay. What I want to prove. So let Z be the number of C's in this matrix. I want to say that if Z equals the flow in this system, this means that it is possible to do if we ignore the A-B condition. So if we ignore this condition, then this is true and also this is true. So if it is possible to arrange some additional C's without the checking the A-B condition, then Z equals flow. Okay, these both can be proven. Let's start with the first one. So assume that Z equals flow. This means that each of these edges from sources and to sinks, or from the only source, but to several C's, and maybe from several R's but to only one sink. So these all edges are activated. So now let's remove them, and instead of that, instead of these 2 edges, we will just direct this edge, and of course fill it with 1 unit of fluid. Okay? Okay, after we've done it, we can say that this is a circulation indeed. But also this is a circulation where for each widget, you definitely have the activated flow. And in each dot, you maybe have an activated flow and maybe you don't. So this is a correct arrangement of the chips, of the widgets. So this is true. And the vice versa is also easier. So assume that this is possible. Then there is a circulation in this system. And then you can replace each activated edge of type Cij with these 2 units of flow because they have to be activated because of our strange condition on circulation, which forces you to have 1 unit of fluid here. So if you replace it back with the source and the sink, you end up with the correct flow of size Z, because for each Cij, the edge should have been activated. So we replace this edge with 2 edges to sink and from source, and they're still activated, so the flow is Z now. Okay, now we have checked where it is possible to do it for A over B. Now we need to maximize it and to check the A-B condition. So we need to find the maximum number of widgets while still the degrees are at most D, and check that D is no more than A over B times flow, where flow is the maximum number of widgets. How do we do it? I guess we just now, even for dots, we're just not using this edge. Okay, we are using this edge, okay? We're definitely using this edge. But we also add this edge to the sink and this edge to, let me think. No, if we do this as I drew this would be really bad because of one simple reason. Yeah, the reason is that actually these two things don't have to correspond to each other. Yeah, so assume that for example, let's draw a picture. So we have this thing and this thing, and the other things are slashes. So the only solution to this instance is 0. You cannot add anything, because if you add here, then you have one widget in the first column. So you have to add one widget to the first row, but there is no possibility to do it. And the same goes for this one. So the only answer is 0. But let's look at the graph which we are resulting in. So we have 3 rows, 1, 2, 3, and 3 columns, 1, 2, 3. We connect the first row, the second row with the first column, which corresponds to this pair. And we say that we add this edge and this edge. And no, the edge from the source looks like this. And for this place, we have this one. Okay, and also we have these edges. Okay, in this picture, there is actually a flow of size 1. Yeah, I can draw it. First of all, you send 1 unit of flow here. Then you go through this edge. Okay, and finally you go here. Okay? And this is some sort of disaster because you were not allowed to do it. You see, because actually this edge can only correspond to this edge, but we paired it up with this edge, and this should not be allowed. So instead of that, we shouldn't direct it to the vertices of columns and rows. Instead of that, we should create 2 fake vertices. Let's call it U21 and V21. And we direct it like this, and like this. Yeah. And here we can, let me think for a while. Actually, I don't think, I don't think we use this edge. Okay, we just have the source and the sink. Okay? And the same goes for this pair of edges. So we have U32, V32. We have the source to the column vertex, to the row vertex here. And finally, here we have this thing and this thing. So there are 2 cases. If we use this, if we put a widget here, Then we have to activate this thing. Then it goes somewhere here and adds 1 to the capacity, to the flow of this column. And so we have to somehow balance it with flow from this vertex. And the same goes here. We have to balance somehow with the flow of the third column. And the second case is we do not use this place. We do not put a widget here there. In this case, they're just like slash. Nothing is possible here. Or no, it doesn't work. Maybe it doesn't work. Yeah, you see, I still can do the same thing. Yeah, I can pair up this vertex with this vertex, can't I? Yeah, I can just direct this flow, and I don't like it. It looks like I messed up a bit. So how can I forbid this? I need to forbid it somehow. Let me think. So we have two vertices, which we need to connect with an edge. But also, if we want this edge to be counted in the maximum flow, if it is used. So how can we do it? Well, this is not as easy problem as I thought. So the first part is actually right. Yeah, I can check whether I can do it. I can find some sort of flow. But the second part is to maximize the sum of green edges. And here where comes the problem, because to maximize it, I need to make some sink and source, but they don't really control the equality of how much comes from here and how much comes here. Okay, let's assume for now that there are no mandatory widgets. All widgets are now allowed for some reason. What to do then? I mean, all places for widgets are allowed. What is the maximum number of widgets we can put here? So usually what we do in these cases, we create some sort of source here. Then we do this. Then we do this. And finally we go into the sink. But this is bad because we would just find the maximum matching. Or not matching, but like depending on these capacities, maximum matching or maximum just taking all edges or something like this. But we are not allowed to do it. Yeah, because we need these degrees to be equal. Okay, this seems like the following problem. We have several pairs of sinks and sources and sinks. And we need to find the maximum flow such that from S1 it goes to T1 and from S2 it goes to T2. Maybe it like intervenes here, but still the flow coming from S2 should be equal to the flow coming to T2, and the same for S1 T1, and the same for all other pairs. Is it possible to solve this problem of maximizing maximum flow with assigned pairs of sinks and sources? Or it's not really possible to do? This is not like a problem which I heard a lot of. Okay, I agree with two things, that the problem is much harder than I thought, and that I actually did not solve it during the contest. So today I actually wrote this contest virtually with my teammates, and we did not participate very well. And in particular, I thought that I solved this problem, I asked my teammates to write it, but they did not, and it seems to be a good decision that they didn't write this problem, because we would just get the PA because of this issue. So the problem is we have some sort of so we have a circulation. We need to maximize the sum of flow through several edges of the circulation. So this worked. This method worked in the previous case because we were only good with maximum flow. So if the flow equals to z, so all edges are activated, then we are fine. And if it is not, then not. But sadly, we cannot afford the same here. So we have some edge. Okay? We have some edge. It is activated. Okay, so we also need this flow go through CJ and RI. After that, it should somehow come here. Okay, this is clearly a circulation. Okay, since I don't know, what we will do here is we will read the editorial, and maybe it will shed some light on this problem. Okay, I have an editorial. Let's look what the authors, or not authors. It's an unofficial analysis. So what maybe some participants recommend to do here? The solution is a circulation in a flow graph. Yes. Oh no. It seems that we need to find maximum course circulation, and I don't know how to do it. maximum cost circulation. Okay, let's Google it. Okay, I see some MIT lecture here. Let's look. The minimum cost circulation problem. Oh no, finding the minimum cost maximum flow is equivalent with finding the minimum cost circulation. Okay, let's see how... I'm not interested in this part. Okay, and in this part. Let's do this part. So consider network G for which we want to find the minimum cost circulation. We add a source S and a sink T to the network without any edges to the rest of the network. Rows. We just add them. Okay, I guess usually min cost max flow is with positive weights. And we here have sometimes negative weights. Can we do something with it? Okay, I need now to find something about minimum cost maximum flow. Okay, I found some blog about minimum cost maximum flow. And it forces me to... It only works if we have no negative cycles. And which is a problem because... Like, I simply don't know how to find... Okay, so we will have some negative cycles, won't we? We want to... Hmm. What to do if we have some negative cycles? This is some craziness. So this is min cost max flow with negative cycles. Hmm. MCMF? No, 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 not today. Okay, let's revise. So, do I really need to cancel negative cycles or something like that? So I want maximum cost circulation. So I need the minimum cost circulation in inverted graph. And obviously I will need negative cycles. Yeah, because any flow is sum of several paths and negative cycles, and since I do not really need any paths, I only need cycles. So this is just a matter of finding negative cycles. So I need to find, I have some graph. I need to find a negative cycle of minimum length, of minimum of minimum of minimum cost, don't I? Let's make an example. Okay, so for example, here I have something like this. Okay, let's make it harder. Something like this. Yeah, so I have R, C, thing, thing, thing. Yeah, and I really just want to make this cost -1, this cost -1, and this cost -1. In this case, this is just minimum cost circulation. Gross. Great. A tiger will solve the problem for us. The tiger. No, 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 no. No. Oh, cycle canceling algorithm. Negative cost cycle in a residual graph. How? Klein cycle canceling algorithm. This is great. But it is really slow. I do not want it. This is not nice. This is not nice. Network simplex method. Are you sure about that? Okay, maybe I will just use. Maybe I just need to use my linear programming. Maybe I just need to use my linear programming and. Okay, it worth a try, I think. So let's start writing the code. Okay, what did I mean? I will just use simplex method. Yeah, what it says. Yeah, it says that for each. No, I actually don't want to do it because linear program will not be happy if there are 1600 vertices. It will lead to 106,000 variables, and we do not want to do it. We do not want to do it. No, no. Simplest method is not applicable here. Oh, topcoder, why? Why is there a link to topcoder? Bye bye. So I really can't find. Let's just write our query. We need min cost, max flow, negative cycles. How do I find the cycle of minimum length or minimum weight? And if I don't do that, it will be slow. And slow is not what I need. We do not want to use push relabel. Why simplex? Why is it always simplex? Push relabel. Okay, I really want to solve it during the contest. So maybe I just find any negative cycle. Not the minimum one. Guys, I'm not happy. I'm really not happy. Post scaling MCMF. What is MCMF? Ah, MCMF is mean cost max flow. Okay. How to find minimum cost mean cycle? Okay, we can find the minimum cycle in n cubed time. For every vertex, we run Dijkstra and build the shortest path tree. But Dijkstra don't work. Oh, case of negative cycles. But okay, I understand. No, I don't understand it. Shortest path 3 is just something which doesn't work here. Negative cycle. Negative cycles can be found by using the Bellman-Ford algorithm. This is really nice. This is really nice. Okay. I think I will not get a polynomial algorithm today, so let's think. The maximum circulation is something like this. Okay? And what time do I spend to find it? Something like VE, so like 80 times 1600. Okay, this is already huge. Yeah, because this is something like... And this is not over. Or is it? Maybe it is over after that. But this is such a gross. So, what we do here is some sort of Ford-Fulkerson algorithm. Also, negative costs are only on these edges. Actually, they are only on these edges. And this is kinda nice. Yeah, it's really nice because actually I just need to find a path from a vertex to this vertex. Just some path from here to here or from here to here. Any path, not just minimal. And it can be done Okay, I have a graph, and I just need to find any path from one vertex to other vertex for several pairs of vertices. Can I do it fast? Okay, actually I can shrink this graph to a single graph. Yeah, I just can contract the green edges. So now I just need to find a cycle in the graph, don't I? Just find any cycle in this graph. Oh man. Any cycle in a graph? Okay, what about these strange edges which are already activated? What about the strange edges which are already activated? Okay, I need to find a cycle through a vertex which is still not activated. Okay, this can be done via top sort in O of m plus n time. I'm so unhappy right now. So what about activated edges? So I guess we need some circulation, and then we fix it gradually. So in the beginning we find some circulation, and it can be done with d-nits. After that, no, actually I cannot do it. Yeah, it's not good because yeah, it's bad. It's bad because yes, all these edges are of negative cost, but after some twiggling, I might get a positive edge. Yeah, so if I have this edge with a positive, with a negative cost, after going through it, there is a residual edge of positive cost, which goes like this, and these are not allowed. Okay, no, this doesn't work. This doesn't work. Okay, I guess I just need to find a negative cycle. That's it. Just find any negative cycle. Hope for the best. Jesus Christ. Nice and easy problem about negative cycles and maximum flows. Okay, we have some sort of... First of all, we need to check whether there is to find max flow. Here. And how can I do it? I will just write I guess it's called Riemann-Karp algorithm, isn't it? Oh, of course not. It's not Riemann-Karp, it's... I forgot. Okay, for the sake of completeness, I need to... What is it? For the sake of completeness, I need to find the name of this algorithm. Okay, Edmonds-Karp, of course. I will just call it Edmonds-Karp. Okay. What does it do? It has... We have struct flow edge, which consists of start, finish, capacity, and flow. Yeah, and now we need to sort of add edge. How do we add edge? So int start, int finish, int capacity. We say that f dot size is the number of the new edge. Then we f dot in place back. No. I actually don't know if we can write such initializer with brackets. Maybe we can. What is my C++? It's 14. Yes, it's 14. Okay, let's try it. Okay, it's kind of worked. Okay, maybe let's also make it store all edges. And let's make pair int bool, so it says which edge and in which order. So okay, maybe even just int. How do I do it? With just int. So if the edge is went in the right direction, I say that edge s dot push back edge f. No, not edge f, just edge number. And if the other direction, then this thing edge number. So this will be a negative number, and this is how we will understand that the edges went in the other direction. So int max flow. And here we just find the minimum cost. No, not minimum cost, just maximum flow. So we do while true. So we sort construct the BFS tree. BFS tree. What after that? So we say that vi BFS tree equals find BFS tree. And if I think we can actually pass S and T here. I believe so. Because why not? So if yes here, and if BFS tree T is not -1, then there is a path from S to T. And we go through this path. Okay, not only I want to find the BFS tree, I also want to find the edge through which I went. So I need here pair int. And the second int is the number of edge. So here I say int n const return edge. Why is it called edge? It should be called G, for example. It's just the adjacency lists. So find BFS tree. So here I propagate. So if this is 1, then we break. Here we say int ans equals 0. Here we return ans. And then we say int. Actually, I can make a tuple. So let me extract BFS result. So here we store parent. Capacity, residual capacity actually. And we store edge number. So of course here we need a BFS result. And here we check that it has a parent. But otherwise we say that int to push equals bfs3 t dot residual capacity and x equals t, and while x is not s, we do the following. We say that we take, let's make a function which pushes some flow through an edge. It int edge number and int flow. So if edge number is at least 0, we push f edge number dot push flow. Else f not edge number dot push minus flow. Okay, how do we push? We just say that flow plus equals flow. So we say that we push flow edge number and flow to push. Then we jump from x to bfs3 of x dot parent. Great. And finally we say that ans plus equals to push. Also, I will need, so in the bfs3 I will need a function called traversable int edge number. So if edge number is at least 0, I will just check that f edge number is traversable. Maybe it's traversible. Yes, I believe it's traversible. But if it's not, you can make fun of me. Else return f not edge number dot inverse traversable. What is traversable? This means that flow is less than capacity. And what is inverse traversable? This means that flow is greater than 0. Great. Now, when we have done this, we can construct the BFS tree. How? Do this. We make a queue. And while q.push of s and while q.size. Also, I would like to say that ans s equals something. What is something? It's just like s infinity minus 1. Infinity will be this, minus 1 will be minus 1. What's wrong? Can I do like this? No? I really need to do this? Okay, as you wish. So while q.size int x equals q.from, q.pop, then we iterate through the edges of x, not from of x, but of fx of gx. Yes, so if not traversable edge number, then we just continue. If why? Okay, I needed to put a const here. So if it is traversable, I need to check if I have already checked this vertex. So if I say int 2 equals end of edge number. How do I find the end of an edge? So if edge number is at least 0, I return f edge number dot t. Else I return f edge number dot s. Great. Now if ans2 dot parent is not -1, I can do it like this, I guess. I think I can. If it is -1, I continue again. Otherwise, okay, let's also find capacity. And here I needed to write like this. A residual capacity, okay. Actually, here I would like to say return residual capacity of edge number is greater than 0. Okay, let's find residual capacity. If the edge number is at least 0, then we just need to subtract capacity and flow. Otherwise, we just need to return the flow. Okay, we say that residual capacity, or just C equals residual capacity of edge number, and we say that ans2 equals, so parent is x, residual capacity is C, minimum of C, and current residual capacity, which is ans x dot residual capacity. And finally, the edge number is edge number. Okay, now when we have found this, why doesn't work? Because of this, and since I used minimum, I need to add algorithm. I finally q.push to whatever, and finally returns. Okay, we have written the Edmonds-Karp algorithm. in only an hour. So now let's make some canvas for the solution. I hate this, I hate this, I hate this, I hate this. I really hate this. Hate this, hate this, hate this. This is awful. This is abomination. Bad. And the worst of all this is this problem. So we read N, A, and B. So how do we solve test? So we try to read N, A, and M. A and B, of course. So if we do not succeed, we return false. If N equals 0 and A equals 0 and B equals 0, then also we return false. Otherwise, we need to read the test. I guess we use a vector of strings. We read all strings. Then we print case test number colon space find ans. Not find ans. I guess let's return -1 if it is impossible. So if int ans equals find ans of v, a, and b, if ans equals -1, print impossible, else print ans, and then print line break. And here we need to find ans with vector of strings and int a and int b. Great. First of all, we need to find z, which is a number of already used chips. Not chips, but how it's called? Widgets, components. So we also make vector bool. And possible. So if Sij equals C. Then we say that plus plus C, and already ij equals true. Else if Sij equals dot, then possible ij equals true. Nice. And we immediately say that if a equals 0, then if z equals 0, we return 0, else we return... What's wrong with you? Why are you jumping like this? Return -1. Now, we're assuming a is not 0. Then we iterate from 0 to n, and we try all possible capacities of this green edge. So we create an endband scarp. And we need to find to write the number of vertices. Yes, so the number of vertices is like n plus 2. So 2 times n plus 2. Okay, I guess first of all we have 0 and 1 for source and sink. Then we have I plus 2 for array. And then we have I plus 2 plus n for CI. Now we need to construct it. We will call it green edges. The element scarp also needs to be initialized. We can do it like this. Great. So here we construct this graph. First of all, we add green edges, which are initially zeros. So we say green edges dot push back Edmund scarp dot add edge of from 2 plus I to 2 plus n plus I of capacity 0. Also, we have a source, we have a sink, and we need to add an edge. For each pair of already put components. So if already ij, then I add an edge from I to j of capacity. No, not like this. And this is actually incorrect. I add from source to the column 1. So j plus n plus 2. And from the row, which is I plus 2, to the sink 1. Else, we just add else if possible ij, we just add from I to j. Okay. What a nice problem. So what do we do here? First of all, we go through. Actually, I also want to say that int ans equals -1 and return ans. So here, what do I do? First of all, I need to go through all edges. Green edge number of green edges. And I say that Edmund scarp dot edges green edge number dot capacity equals d. Yes. What next? After that, I say that collected flow plus equals Edmund scarp dot max flow from 0 to 1. So if collected flow turned out to be less than z, then we continue. Fine. Okay, now we only need to find the mean cost circulation. Okay, let's think how we do it. We just need to find a negative cycle, and if we'll see it, we need to go along its edges. How is it possible? So we have a negative cycle. We see a negative cycle. How do we find a negative cycle? We store edge lists for each vertex. Actually, I think we will need. So let's say that all vertices in the beginning are reachable. They are all zeros. Yeah, let's assume that there are no negative cycles. Yeah, in this case, if I run let me think. So if there is no negative cycle, I can run Fort Bellman n minus 1 times. Okay? If there is no negative cycle, then by the end, I will get just the minimum distance from some vertex to some other vertex. So minimum cost path between these vertices. But if I make one more iteration and something changes, this means that I definitely have a negative cycle. Great. How do I find it? Well, for each vertex, I want to store the last event which led to it changing. Yeah, so it was something like alpha, it became less than alpha, then something led to this event. And actually this changed on the previous turn, yeah, because otherwise it would be strange. So I go back, and finally I need to make a cycle. Does this cycle have to be a negative one? I think yes. Or no. So is it true that if I have done something in a cycle, this definitely means that I have a negative cycle here? It seems so. Okay, let's try and write it. So let's call it struct Fort Bellman cycle destroyer. What does it do? It kinda has the same vibe, low edge F, but this time I will only. Okay, never mind. I have several edges. Okay, let me think. Yes, it's same. Actually, much of this is same. I guess I could even make a special struct called flow graph, and these both things use it. Use it. Yeah, I think it's legit. Let's structureize our solution. So we have struct flow graph, which has these like fg, Actually, all of this, I think all of this can be put in the flow graph. So Edmund Scarp just stores flow graph. So Edmund Scarp runs graph of n. Here we have this thing. And we call everything from the graph. Graph.traversable, graph.g, graph.end, graph.residual capacity, all this stuff. Okay, now. Okay, so let's fix a bit here. So what I really have is a graph of Edmund's carp. What I really have here is Edmund's carp graph. I even think I can push flow into the graph. Yeah, this can be put here. Okay. Here I can do it only if elect flow is less than z. Or even if this thing is empty. Yeah, because Ford-Bellman cycle destroyer also contains a graph. So here we say that it is 0. Okay. So now we have to build a destroyer here. How do we build a destroyer? So it needs to use some edges from the Edmund Scarp, and if the edge is activated, it activates it. So actually we just copy, I think we just copy the system from the Edmund Scarp. Yeah, so let's edge numbers of n of n. Okay. Here we say, so if it is possible, admin_scarp.add edge and edge numbers ij equals this thing. So now we construct the destroyer. So destroyer equals the destroyer of size 2 times n, actually. Then we go through all edges. So first of all, we put the green edges, I guess. Let's call it red edges. So red edges are green edges of the destroyer. So we say here that red edges I, sorry, no, incorrect. Red edges I equals destroyer dot graph dot add edge from I plus n to I. So actually it should be n plus I here. Yeah, also now edge also has a cost, doesn't it? Yeah, so now I need min cost flow edge. And now it is also of a cost which I will call A. Okay. Ah, gross. So I cannot use graph here. I cannot use graph here. Okay, this is fine. I can just store. I think I can store them separately because I really don't want to store it in the graph. So here we have int add edge from to capacity and cost. So we say costs. We say graph dot add edge stc and we also say costs dot pushback a. And here we return this thing. Great. Destroyer dot graph edge dot add edge I plus n I of capacity d and of cost 1. Then we go through all the edges here. I don't want to do it like this. So I go through all edges. So if already ij, I just add. I think I need to I need to also give the capacity. Not the capacity, but flow. I need to pass the flow here. So here I have int flow and int a. So here I say int edge number equals this. I say graph dot f edge number dot f equals f, and then return edge number. Great. Here I pass Edmund Scarp. Dot graph dot f green edges I dot f. Yes. If already, then destroyer dot add edge of from I to j plus n of size of capacity 1, of flow also 1, and of cost 0. Else if possible ij, then it is possibly in the flow or possibly not. So we need to check it. And for that, we look into our advanced Scarp. So capacity is still 1. We look into Edmond's Scarp dot graph dot f. Now we look into edge numbers of ij. Now we here look into the flow, and finally 0. Actually here the cost is -1. I want to find the mean cost. Great, I have constructed this thing, and the collected cost is -z. So here I need to do two things. First of all, I need to increase the capacity of all red edges. So I go through all red edges. And I look into destroyer. Into the graph. Into the edges. I look into the red edge. I look into this, its capacity, and I say that it is D now. After that, I need to find the collected cost. Destroyer dot mean cost circulation. Yes. Now I want. Oh man. Oh man. I actually need the same thing for the destroyer edge numbers. Okay, this is fine. So collected cost plus equals destroyer means cost circulation. I need also this thing. So I don't need to find the answer. Actually, no. Actually, not. I only need to find. I mean, I don't need to find the assignment. I only need to find the number, and this is easier. So okay, no, do not need to do it. So we need the collected cost with sign minus. If I multiply it by A and divide it by B, it should be at least D. So if this is true, then answer equals minus collected cost. Great. And the final thing is to find the minimum cost circulation in the graph. I'm dead inside. Okay. So how do we do it? First of all, while true is not correct, because if I didn't find anything, here I have a break. Okay. So while true, I need to do something. So what do I need to do? I need to find minimum cost cycle. Okay. This is still kind of BFS result, I guess, because I need a parent, I need a residual cost this time, and I need an edge number. No, I do not need a cost. Yeah, I need a cost. Yes, I need a cost, but I can calculate it during the backtracking. Actually, I also have an error here. I also have an error here. I think I need something like cycle finder. No, I have a BFS. For BFS, it is right. It's not right for Fort Bellman. So, okay, let's construct it. Vector BFS result. Tree equals, like, it's not a tree, but we will find. We will be fine with calling it a tree. So this is Fort. Find Fort Bellman tree. No, I think I will need a negative cycle just. Find negative cycle. So if tree.empty, I just break. Yeah, otherwise I need to push through this cycle. Yeah. I don't think I actually need this thing. Yeah, I just need parent. Actually, just need a list of edge numbers. I do not need anything else. Okay, let's just find negative cycle. It will just find the numbers of edges. So here, int cost equals 0, int capacity equals 1 in 9, and now we go through edge numbers over the tree. So int find cost. So if edge number is at least 0, return costs of edge number. Else return minus costs of edge number. Great. So here I say that capacity is minimum of capacity and graph dot residual capacity of edge number. Also, cost equals plus equals find cost of edge number. Great. And finally, we push it. So we say, first of all, we say that ans plus equal cost times capacity. Then we say that we need in the graph to push some flow edge number capacity. And return ans. So now we only need to find a negative cycle, which will be easy. I believe in it. Great. So how do we do it? For each vertex, we need to store its previous vertex, or like previous edge, I would say. Yeah, we need to store its previous edge. So vector int previous edge size L, and in the beginning it just stores itself. Or just like 1 in 9. Okay. Also, we need to store the potential. Which is like phi. And it is 0 in the beginning. I think I can just store 0. It will be okay. So I do the following thing n times. Something changed and I is less than n. We say that something changed is false. Okay. Let me say that something changed is a vertex. It is equal to -1. So here it is equal to 0, for example. Here say that's changed is not equal to -1. Then I say that it is -1. And in the end, I want it to be not -1. So if changed equals -1, I return nothing, or else I do something. So let's see what I do here. I iterate over all edges. Yeah. So I go through all vertices. I go through all edges. I check if traversable, if it is traversable. And if it is traversable, I also check if it is possible to reduce the potential. So I say that new phi equals current phi of my vertex j plus find cost of edge number. And if new phi is less than phi of, I also need to find the number of this vertex, which is graph dot end edge number. So if it is less than phi2, then phi2 equals new phi and changed equals 2. And also previous edge of 2 equals edge number. Okay, now I need to found all edges of some cycle. Starting with changed. So what do I need to do? I start with changed, and I go back, and I go back, I go back until I finally see some vertex which I have already seen. Okay, this is not that hard. So I say vector int step, and step is when I saw this vertex in my ans. So while true, I do the following. Also, I have int current. I can just use changed as current, but I will not. Okay, while true, I do the following. I say, so if step current vertex is not -1, then I found a cycle. what do I do then? I go through int I equals step current vertex. I is less than. Actually, I can just say return a vector int which is defined by 2 iterators. The iterator ans.begin plus step current vertex and ans.end. Great. This is if I have not seen this vertex. Now we assume that I have seen this vertex. Then I jump back. I say that now step current vertex equals ans.size, ans.pushback. The edge previous edge of current vertex then I say that current vertex is graph.end of not current of not this previous edge. But I have written it. Actually, this can work. This can work. Although it won't. Let's begin with the compilation errors. Push flow must return a value. No, it shouldn't. Zero, impossible, impossible. 12, impossible. It's all incorrect. But let's start with something easy. This one. So why is it impossible? Zero. Let's look into the solution and we will find some mistakes, some errors. Okay. What? Collected flow? Why is collected flow greater than 1? It is incorrect. Collected flow couldn't be 1 because we do not have like a path from S to T. Let's see if it found it. So it actually found it. So D is 0. Get it right, yeah? So green edges are 0 and 1. So I bet it cannot. Ah, now D equals 1. Okay. Okay, now D equals 1. And now it should work. It should work. Ah, I need to subtract. I need to subtract Z, actually. Let's try it. Let's try it with subtracting z. And here we need to put, okay, if ans equals -1, return ans -1, or else return this thing. Restart. Okay, now it is 6, which is still not right, but it's better. Okay. So it found this. Now we need to destroy some cycles. We need to destroy some cycles. Okay. Ah, it's not correct. It is an incorrect inequality. So let's rewrite it. So what I need, so if what? Why is it -1 and not -2? How is it possible? Ah, no, I don't get it. I don't get it. Actually, it's not -z. It's not -z. It's the sum of all destroyer edges. It's the sum of all destroyer edges. Okay, I don't understand it anymore. I think we need to forbid touching that edges which are in the array already. Yeah, we need to forbid touching them because otherwise maybe the circulation might cancel them for its own good. And we cannot allow that. We cannot allow that. So let's just forbid them somehow. So to do it, we need to add just an array forbidden. Graph n costs, yeah, forbidden, okay. So bool forbidden. And we say that forbidden dot pushback forbidden. And here check forbidden. Return, so if edge number is at least 0, return forbidden edge number, else return forbidden not edge number. And when we check traversable, we need to check two things. Bool traversable. We need to check not forbidden of edge number. And we need to check that it is traversable in the graph. Okay, so this is the first point. We add it here. So this is not forbidden, and this is forbidden. Okay. What next? What next? Actually, next thing is what is next? I need to find the sum of the green edges. So I say that it is 0. Then I go through all green edges. And I subtract the flow through its edge. So this is, as we like a lot, Edmonds harp dot graph dot f green edge number dot flow. Okay, great. Great, 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 great. Not great. I need to say that it is not forbidden. One. It is better than nothing. Now it is all fine. I think we can even submit it because I'm tired. I really do not want to debug it. And this is upsolving, so we are more than fine to send it. So problem D, submit. And this tasty thing is going to be submitted. Oh. Wrong answer. Just wrong answer, and I go to sleep. You are not compliant with C++11. So, what I'm supposed to do? Okay, I can just, it's fine. I can say const int inf equals 1 in 9 and replace it with infinity just everywhere. Okay, we can send it again. One more minute of positive weighting. It can actually tell. However, it shouldn't. It can be because there are plenty of places where a bug could be. But tail is, it shouldn't be tail, I think. Why don't you have C++ 20? Yeah, so it cannot convert from initializer list to a structure. This is not really good, but we will fix it, of course. Who are we to disagree? BFS result int parent equals -1 int residual capacity equals -1 and int edge number which equals -1. Parent residual capacity and edge number. Okay, then we remove this thing and we find everywhere where we used an initializer list. Also, I guess this will not work. I think this will not work. Yes, so because we need a flow edge structure. So we have to write some boilerplate code for this to work. Now I can use place back because there is a constructor with this signature. This is kind of C++ 14, but I'm really raging that there is no C++ 11 and I have to spend time on this. So here, for example, we cannot do it. We need to run a constructor. Here we need to run a constructor. Okay, I guess now it's clear. For our C++ 11 compiler, ANSI C have we gone in ancient times whatsoever. Okay, we just need to wait for 2 minutes for another one. Compilation error. No, not favorite. We kinda sucked during the finals. See? Like 56th place is not good. It's really not good. And we didn't solve problem J, which was solved by 134 comments or teams. This is not nice. This means that somebody is overpriced. Or is overpricing themselves. Dude, 56th place. This is just so demotivating. Accept it. Accept it, guys. So this person has written shitty. Sorry, my little viewers. Damn main cost. How is it called? It's called circulation, main cost circulation, and Edmund Scarp with no errors. So first try, solve, accepted. And these 2 hours and 45 minutes is a monument to my stamina. Thank you for watching.